We're going to launch right into hypothesis testing. So here we are in Notebook 14, one sample t-tests. Okay. And we start off looking at the bell curve and another very similar curve, the t-distribution. It's very, very similar to the standard bell curve. And for small samples, the t-distribution is more accurate. Okay. So the t-test is the updated version of using the bell curve in statistics. And the earliest hypothesis test did, in fact, use the actual bell curve. But the modern version is the t-test. All right, so get Notebook 14 open and ready to go, ready to take your notes. Pause the video while you're doing that, and then we can jump on in. Okay, so as we launch hypothesis testing, what is it? Well, it's a way to take quantitative data and turn it into a scientific conclusion about a hypothesis. Okay, and it always goes the same way. We set up the null and alternative hypotheses. You'll see that in just a second. So we set up the hypothesis. We simulate a test statistic, and then we calculate a p-value. Now, steps 2 and 3 happen together a lot of times in a single step that we can have Python do. And you'll see that we have some nice features that we can draw on so that steps 2 and 3 will go together. Then we have a statistical conclusion. We either reject the null if our p-value is less than alpha. And by the way, alpha is always 0.05. Not always, but in an introductory statistics class, alpha equals 0.05 is a very good starting point. And don't use anything other than 0.05 unless you're told to do something different. Okay, and then if we don't reject the null, we fail to reject the null. And what's our research conclusion? Well, if we reject the null, we have evidence for the alternative hypothesis. You'll see that in just a second. And when we fail to reject the null, we have no evidence the null is false. And you say, well, isn't that evidence for the null? Well, not exactly. We have no evidence that the null is false. And that's the best way to describe it. And while we're going through this p-value, every single hypothesis test generates a p-value, all right? And the p-value is basically the probability that the null hypothesis is true. That's there's some slight nuance to that, but big ideas. The p-value is the probability that the null hypothesis is true. Okay, there you go. That's hypothesis testing. That's what we're going to be doing. And we're going to start with the first question in the notebook in just a second. Let's go ahead and get the notebook running. And I want to point out this scipy.stats as stats. Okay, so this is important. The scipy.stats is a package that has a lot of these hypothesis testing codes. So we're going to do a lot of stats, right? This is the alias is stats. So stats.something to run these codes. All right. And here's the t-distribution, just like I said. So you can see the red is the bell curve and the green is the t-distribution. And for large samples, you see those degrees of freedom is basically sample size. So as the sample size gets larger, the green almost matches the red identically. And then when DF is smaller, you can see that the green bell gets shorter and wider. And again, it's the green one is the modern one. The green one is the one that is much more accurate for small sample sizes. Okay, and that's just a visual description of what I was explaining earlier. Okay, and so then we have 3 questions, and the first one is, do students take 5 classes per semester on average? Let's jump back into the PowerPoint here. Okay, so we're going to use the class data.csv and the hypothesis. Do students take 5 classes per semester? So that's what the null hypothesis says. So we use H sub 0, and the H sub 0 is the null hypothesis, N-U-L-L. Okay. and H sub A is the alternative hypothesis. So let's talk about the null first. Do students take 5 classes per semester? So what this is, this mu equals 5, mu is the average number of classes that students take per semester. So we have a sample, and we're going to calculate a sample average in hopes that the sample average will closely approximate the population average. And then we'll be able to determine, based on those estimates, whether or not the population average is actually 5, or if is the alternative hypothesis says is different than 5. All right, and I'll show you the code that we're going to use because I said we're using this stats alias, stats.tTest. And we need an array data. That's why we're using the dot column method. Remember, dot column is like dot select, except that we're going to get this num courses variable or column as an array. Okay? And this population mean equals 5, that's just saying this part, right? The letting the computer know what exactly the null hypothesis is that we're testing. Okay, and we'll come back and look at some more results in just a second, but let's get rid of the ink for now and jump in here. So here is our classes table that comes from the class data.csv file. And notice that we're looking at this num courses. All right, we're looking at that column and we're trying to see if on average these students do in fact take about 5 classes per semester. And there are 288 rows omitted, so you'll see that there are almost 300 students represented. Okay. And again, this is the 15 to finish. If you're going to complete a bachelor's degree in 4 years, you must complete about 15 credit hours per semester. And if most classes are 3 credit hours, I know that's not always true, but it's just the best way. So we figure out how many classes people are taking, assume they're all 3 credit hour courses, and then we can estimate if they're taking those 15 hours. So that's why we're coming up with the 5 classes per semester. Okay, so fave stats. We tell it the table, the classes table, and we tell it the column that we want to know the descriptive statistics for. And here we go. We get the mean, the standard deviation, we get the 5-number summary, which is the min, quartile 1, Q1 is the 25th percentile, the median, Q3 is the 75th percentile, the max, we get the interquartile range, we get the sample size of 298. Okay, and the average, notice, is about 5.017 courses. Okay. So we have some data here. And notice, okay, so I'm not going to talk about all of the aliases. We just imported the scipy.stats, so it can be run the way it is in your notebook. Let me take a look at this. I thought I had it right. So from import scipy.stats as stats, and we're importing, oh, I see. We're importing this tTest underscore one samp as tTest. Sorry about that. I screwed up. I wanted to show you that we use this stats. And I still don't have it right. What's the name of this stupid thing? tTest underscore one sample is in scipy.stats, and we are importing scipy.stats as stats. So this, oh, I put one sample, not one samp. Okay, sorry. Oh my, I put one sample, do one samp. And why am I showing you this? Because this is the code that we use. Again, to make things a little easier for you, they imported, this scipy.stats thing as tTest, but the actual name of it is tTest underscore one samp because it's one sample of data. We bring in the array data for the one column, num courses, and we're comparing to a population mean of 0.05. Okay, and what do we get? Well, we get a p-value of 0.0679. Okay, so jumping back in here, right, we get this p-value of 0.0679. And I showed the tTest underscore one sample. It's actually lowercase. Oh, I'm sorry, this is lowercase. And again, remember it's underscore one samp on this. Okay. So what does all this mean? Okay, so what we're going to say, what our real world conclusion is, that look, the p-value is bigger than 0.05. And because it's bigger than 0.05, our statistical conclusion is that we fail to reject the null. In other words, we have no evidence that the null is false. The null is that students take 5 classes per semester. And we have no evidence that that's incorrect. Okay? Now, again, some people would say, well, now we have evidence that students take 5 classes per semester. Well, sort of. But what we actually have is no evidence that it's not 5, that the average is some other number like 4.8 or 5.2. You know, we don't have any evidence for a different number being the average. And so anyway, these university administrators who are looking at this data can feel pretty comfortable. Yeah, students are taking on average about 5 classes a semester, and therefore most of our students, our average students are doing that 15 to finish. Okay, so and all of these steps are required, okay, that when you're doing the project, you are going to need to set up a hypothesis. You can say this in words, okay? You are going to need the code and the results, and then based on this p-value, you're going to have to reject or fail to reject the null. And then you're going to have to say what that means in real world terms. Okay, so all those steps are required when I'm doing a hypothesis test, and your project is about hypothesis testing. So do students get at least 8 hours of sleep per night? Okay, same thing. We're going to look at the hours of sleep per night, and our null hypothesis is that the average hours of sleep, so mu stands for the population average for hours of sleep, and we're saying, hey, we think that mu equals 8. And the alternative hypothesis is no, they don't get at least 8 hours of sleep, they get less than 8 hours of sleep. Okay, so let's see how this works when we jump into the notebook. And you can read this stuff up here. Sorry. So the second question is here, and this is all good stuff to read, but I'm going to jump down here to, here's our null hypothesis, here's our alternative hypothesis for the hours of sleep question. Okay, and we do fave stats, classes, and sleep hours, and we see that the average number of hours of sleep is 7.36. So we're like, it looks like they get less. Okay, so now this t-test, right, which is, sorry, stats.tTest. You don't have to do this in this notebook, but boom, there it is. And also notice that I don't have to do this pop mean equals 8. It works that way, but notice that there's only one option, right? So when I just put in an 8, it's like, oh, okay, you mean the population mean equals 8. So I just have to put the value from the null hypothesis in there, okay? Now, what the Sam Hill happens with this p-value? Check the end of the number, that e to the minus 15. That's scientific notation, so that means times 10 to the negative 15th. So this p-value is really, 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 really close to 0. So let's take a look at how we interpret those results. Okay, so I get a p-value that's very close to 0, so that means that p is less than 0.05, and we reject the null. So we have evidence, and because the p-value is so small, we have pretty strong evidence that the null is false. Why? Well, remember, the p-value is approximately, roughly speaking, the probability that the null is true. Well, there's basically a 0 chance that the null is true, right? I mean, the p-value is so small, so close to 0, we have an almost 0 probability of the null being true, so we reject it. And if we reject it, we have evidence in favor of the alternative. The alternative is that the average number of hours of sleep that students get is less than 8 hours of sleep per night. Okay, so let's look at one more example. Do babies born to mothers that don't smoke tend to weigh more than 118 ounces? Now, we're going to use the baby.csv data, and let's make this point. This is older data, and they're using the weight of the baby as a proxy for good health. That a healthier baby is going to weigh a little more, and an unhealthy baby is going to weigh a little less. Now, in modern days, we do know that it's possible for the baby to weigh too much or too little, like we can err on either side, but basically this is when they're using weight as kind of a proxy for the health of the child, okay? And we're going to want babies that weigh more, okay? So our null hypothesis is that the average baby weight is 118 ounces or grams. I'll have to think about that. But let's jump back into the table. All right. Sorry, and they do the reporting out. And this is almost exactly what I said. Okay. And this is a box plot for the distribution of hours of sleep, so we can see why we rejected the null there, and the p-value was far less than 0.05. Okay, so there is some good information about the previous hypothesis test. And they redo this hypothesis test with 7.5 hours, and it turns out that we reject the null. Why? Well, because we had a one-tailed t-test, and so we cut the p-value in half, and that is less than 0.05. But let's get down to the babies born to mothers who don't smoke. Do they tend to weigh more than 118 ounces? Okay. So we do the fave stats on the birth weight of the non-smoking mothers, and what do we get? We get an average of 124 ounces and a standard deviation of 18 and 2/3, it looks like, or approximately 2/3. So here is our t-test, right? So we're doing the stats.ttest underscore one samp. And I fat fingered that and put an X instead of an S. And it says non-smokers is not defined, although it just did it here. So let me run this cell and then run this one. And so we've run everything, and the p-value is 0.06, but it's a one-tailed test. What does that mean? Well, let's jump back in. Okay, one-tailed test means I use a less than or a greater than rather than a not equal to. Okay, not equal to is a two-tailed test. And then the less than is a one-tailed test. Why is this important? Well, the numbers that spit out of the hypothesis test, the p-values that spit out of the hypothesis test, assume it's a two-tailed t-test. If in fact it's a one-tailed t-test, the p-value is half. So here the p-value is correct. The one that spits out of the test is correct. Here, I chopped the p-value in half to get the accurate p-value. Okay, so when we do that, we get the p-value from the test, which again is a two-tailed p-value of 0.063, but we cut the p-value in half because our hypothesis is a one-tailed hypothesis. So if we have a greater than or a less than, that's a one-tailed hypothesis. And if we have the not equal to, right, not equal to would be the two-tailed hypothesis, but this is the default. This is what spits out. And to convert to this situation, we just cut the p-value in half. All right, and so what's the conclusion? Since the p-value is approximately 0.03, and that is less than 0.05, we reject the null, and these babies on average do weigh more than 118 ounces. Okay, so we have an idea that, yeah, the not smoking does improve the health of the babies. Again, we're using the weight at birth as a proxy for the health of the baby, and we're saying that we have a more healthy baby in the non-smoker group. Okay, so we can do these hypothesis tests with confidence intervals. And let's just take a quick look at that. Oh, and by the way, here is a box plot of the distribution of birth weights. All right, and you can see that it surely indeed looks as though the average is above 118. Okay, so we have healthy babies in our box plot. Now, jumping down to confidence intervals, and you can read about the formula for confidence intervals and what these things mean, but we also have a way to do it. Okay, so what are we doing? We are generating a distribution to try to estimate something, and then we're using this interval along the x-axis as our estimate. And the law of large numbers says that the larger our sample size, then the standard deviation of the bell will shrink, right? So this, how wide the bell is, it'll get narrower and narrower, right? So the law of large numbers says, well, the bell will get narrower, so this estimate will get more and more accurate. Okay, so and the calculations up above, it says it shows you how to calculate t directly, but we know these, and we've known these for a long time. We use them in traditional stats before computers, and so people did the calculations and just produced them for everybody. And they show you how to actually calculate this this t star number. But here's the question, okay? So we're going to go back to what is the average birth weight of babies born to mothers that do not smoke? Okay, so what's important here? Well, we provide this to you and this code to you, and all we have to do is this data, right? They're doing classes.column.number courses. This is starting with the first question, so we're going back to the number of courses. And data, right? We get the mean of the data. STE, that's the standard error. So that's stats.sem data. Again, this is provided to you. So the only thing that we ask you to do is get the data, do SEM of the data, do the TSTD. Remember, we don't just use standard deviation, we use TSTD. That's the more modern version. Okay. Degrees of freedom is calculated for you. We tell it the confidence level. What percentage? Is it a 90% confidence interval? Is it a 95% confidence interval? And then here is the stats.t.interval, right? If we want a t-interval, we just tell it, hey, run a t.interval. We tell it the confidence level divided by 100. Why? Because it's expecting a decimal, right? We give it the confidence level as a 95% confidence interval, but the number that the t-interval function needs is 0.95. So we divide it by 100. Then the df is from right here, and the mean and the STE, are from right up here. Okay, and when we run it, right, it tells us the sample mean, tells us sample standard deviation, but here's the thing, the 95% confidence interval is between 4.94 classes per semester and 5.1 classes per semester. So yeah, we have a 95% confidence interval that the average number of classes that students at UNG take is between 4.9 and 5.1. Well, okay, that's a really nice estimate. Is it exactly 5? No, we don't have evidence that it is exactly 5, but we have good evidence that it's near 5, really close to 5, which is good news. And they show the 95% confidence interval in red. Okay, so let's talk about how to report it. So we're testing this value again. Just like we did with the mothers and the baby weight, the non-smoking mothers, baby weight, mu sub 0 was 118, right? So we take that mu sub 0, that average from the population, which in this case is number of courses taken per semester, and if it is not inside the confidence interval, then you reject the null. Okay, if that value, in this case 5, is inside the confidence interval, then we fail to reject the null, right? So we did a confidence interval and we found an interval that included the mu sub 0 value of 5. Since 5 was in the interval, we fail to reject the null, and therefore we have no evidence that the average is different from 5. And what do we conclude? We conclude that the average number of courses that students take per semester is not significantly different than 5. Okay. Again, some people will shorthand this. It's not quite accurate to say that we have evidence that the average is 5. Again, what we have what we have scientific evidence for is that the average is near 5, very likely to be near 5. And we don't have any evidence whatsoever that it's different than 5. Okay, so that's why, that's how we do hypothesis testing with confidence intervals, and they both use the same technology, the t distribution, which is very bell-shaped.